Organic Chemistry, Lecture 3, Bonding. Before we begin our discussion of organic reactions and synthesis, we need to have a quick review on what it means when we say chemical bonding. Well, bonding is based on orbitals and electron interactions between atoms in compounds and molecules. So let's go over some basics and fundamentals, starting with atomic orbitals and quantum numbers. The first number we have to discuss is the principal number, which is denoted by the letter N. This is talking about the energy level of the given electron. The second is the azimuthal number, L. This denotes the subshell that the electron resides in, and the values for which range from 0 to n minus 1. So it's always going to be less than n to 0. The magnetic quantum number, ML, denotes the orbital within the subshell that the electron resides in. And these values are always between -1 to 1. So it's always going to be -1, 0, or 1. This will signify the orbital shapes, and there are 4. The s orbitals are spherical. So if I were to draw an s orbital, it would look something like that. P orbitals are dumbbell shaped, and there's 3 of them, based on the x, y, and z axis. So if I were to draw these out, they would look something like that. And if I were to put a comparison out, in 3-dimensional space, these would each correspond with one of the axes. So if I have x, y, and z, I would respectively have pz, px, and this one right here, and py. So those are the 3 shapes you'll see for p orbitals. D orbitals are 4-leaf clovers. So imagine a p orbital except with 4. And f orbitals have 6. Note that for d orbitals and f orbitals, you rarely will be tested, so honestly, you can probably just ignore these. The last number is the spin number, m sub s. The direction the electron is spinning is noted by -1/2 or +1/2. A good way to keep all these straight when you're looking at them, so there's NL, ML, and MS. A best way to keep these straight is to think about an apartment complex that has duplexes. So if this apartment complex has multiple floors, the floor that the room is on is going to be noted by N. The room is going to be noted by L, so the room on the floor. M sub L is going to denote which room within the room the person resides in, and the spin number denotes which of the 2 people is in that specific room within the room. So think of it as a more generalized description to a more specific description. However, we need all 4 to correctly assess which electron we're talking about. Now that we've talked about atomic orbitals, let's go into molecular orbitals. These are orbitals, as the name would suggest, that are formed when 2 or more atomic orbitals combine. So you've got 2 atomic orbitals that are overlapping or not overlapping. If they overlap, they create bonding orbitals, which have lower, more stable energy orbitals. So this is formed when the orbital wave functions are the same. So if I were to have an overlap like so, this would create a more general overlap. These are more stable since they have lower energy, and it's going to create a bond between 2 atoms. Conversely, non-bonding orbitals have a higher, less stable energy orbital, and this is formed when the orbital wave function signs are different. So if I were to go back to my initial example, If these signs were different, then they wouldn't bond, and they would actually oppose each other. So when I say that they would oppose each other, they would actually almost repel each other. So as you can see, there is no interaction between the two. Just because you have orbitals that are free to bond doesn't necessarily mean that they will bond. The wave function and the orientation is all going to take effect. There are two types of molecular orbitals, sigma and pi bonds. Let's talk about the first. Sigma bonds result from a direct overlap. These are all single bonds. So any single bond and one of multiple bonds, so double or triple bonds, have to be a sigma bond. There has to be a direct overlap. Pi bonds, on the other hand, are from side-to-side overlaps. These are each subsequent bond after the first single bond. Note, these can't exist independently without a sigma bond because they are weaker than sigma bonds. Let's draw some of these out. In the previous slide, I drew a sigma bond for you, but a sigma bond is when I have two orbitals that are directly overlapping. This is going to create a head-to-head interaction. A pi bond, on the other hand, is a little different. If I have side-to-side overlaps, like so, these bonds are going to interact and form something loosely based like that. So, if I were to have an alkyne complex of some kind, this is going to be comprised of one sigma bond and two pi bonds. So it's stating that there is one direct overlap and two indirect overlaps. Hybridization. This is formed by the mixing of different orbital types. This also explains why certain bonding behavior is observed, regardless of what you would expect to see. There are three types in particular. sp3 hybridizations are found in alkanes. They have 25% S character and 75% P character. sp3, as the name would suggest, is noting that there is one S and three P's that are hybridizing. So if we go back to our drawings, we remember what an S orbital looks like and what a P orbital looks like. When these hybridize, you're going to get something that looks like that. sp2 orbitals are found in alkenes. They have slightly more S character than P character. sp orbitals are found in alkynes, and this is almost a 50-50 ratio. So the best way to remember these are sp3s are in alkanes, sp2s are in alkenes, and sps are in alkynes. For all intents and purposes, on the MCAT, this will get you by. Sometimes you may be asked about the S and P character in each of the orbitals. Just know that for the more P orbitals involved, so the more P orbitals that are hybridized, the more P character it's going to have. And if you want to calculate the exact ratio, you can just look at the hybridization to figure it out. So for example, sp3 has 4 hybridization orbitals, and 3 of which are P. So that's going to be a 75% ratio of P and a 1:4 ratio of S. And the same goes for the rest. So sp2 has 3 total and 2 P orbitals, giving you about a 67%, and 1 S orbital, giving you a 33%. And lastly, sp. This is in a direct 50-50 ratio, so it's 1:1. So both of them are going to be in a 50% ratio. So all in all, you actually don't have to memorize the character. If you understand what the name convention is talking about, you can calculate it for yourself. The last subject we're going to discuss in this lecture is resonance. This is the delocalization of electrons within a molecule. These cause shifts in the structure spontaneously and constantly. Because of this delocalization, it's going to add to the general stability of the compound. And obviously, as with all things in nature, the most stable, lowest energy configuration is going to be preferred. For almost every organic molecule, you're going to experience some kind of resonance. And resonance is also going to alter what sort of reactions you're going to see. If I were to draw out a very simple system to discuss resonance, it would look something like this. So I'm going to draw out a very basic compound. This is going to be CO3. So CO3. Just like that. So if this was the orientation I noticed, this thing would actually fluctuate. So electrons would bounce around in the system. Like so. As you can see, it's constantly juggling around. And it's going to rotate around consistently, like so. And as you can see, this thing is going to bounce around constantly. Because of this, this electron is delocalized amongst the 3 bonds. So if I really wanted to draw this out, it's usually noted something like this. So every one of these bonds has some loosely affiliated double bond characteristic. Keep in mind that resonance is going to add stability, so compounds that have a better resonance are generally going to be more stable. That covers our review of bonding. Please join us in the next lecture as we talk about how to approach organic reactions.